In this lesson, we're going to review all of the ideas from Chapter 7 so that you are prepared for your midterm. So first we have some basic integration review. This stuff won't come up explicitly, but it might come up as part of another part of a problem. So for example, in the section about improper integrals, you may have to evaluate an integral using a U substitution. Now technically part A could be figured out two ways. It could be figured out using a substitution, or it could be figured out using long division. I'm going to show you the substitution. So let U equal x plus 10. du is equal to dx, and x is equal to u minus 10. Now when you make a substitution, you also have to change your bounds. So if x is 0, u is 10, and if x is 5, u is 15. So this becomes the integral from 10 to 15 u minus 10 over u du. And so now divide both terms in the numerator by u, and we'll have 1 minus 10 over u. So that's u minus 10 natural log absolute value of u, evaluated from 10 to 15. So that will be 15 minus 10 ln of 15 minus 10 minus 10 ln of 10. That's a lot of tens. So when that negative distributes, we end up with 5 minus 10 ln of 15 plus 10 ln of 10. With substitution, often the hardest part is picking what to substitute for. In this case, let u equal the root x inside the sign. Then du is 1/2 x to the negative 1/2 dx, or 2 du equals 1 over root x dx. So you can replace the 1 over root x dx by 2 du. And this becomes the integral of sine u times 2 du. It's so simple. 2 integrals of sine of u, and the antiderivative of sine of u is negative cosine u. So that's negative 2 cosine of root x plus c. The next technique you'll have to recognize when to apply is integration by parts. This is frequently performed when you have a product of two functions. So there are the basic pick uv ones, there are a few where you have to do a clever thing like let du equal dx, and then there are those tricky around the world ones. We'll have an example of each of them. So this is the most basic one. Usually you let u equal the thing who goes away when you take its derivatives repeatedly. So u equals x, du is dx. You let dv equal cosine of 2x. And the antiderivative of that will be 1/2 sine of 2x. So that will equal uv. So 1/2 x sine 2x minus integral of v du. So 1/2 sine 2x dx. So that's 1/2 x sine 2x minus 1/2 times, so the antiderivative of sine of 2x will be negative 1/2 cosine 2x. Now plus c, and just multiply those negative 1/2, and our final answer is 1/2 x sine of 2x plus 1/4 cosine of 2x plus c. So often you let u equal the x or the x squared. So one other way you can tell what to choose is the thing you let be dv must be something that you can easily integrate. And notice that here ln of x is not something that you can easily integrate. So you're forced to let u equal ln of x. When you do that, du is 1 over x dx. dv is x to the 3 halves dx. And then v is x to the 5 halves, coefficient 2/5. So remember the formula is uv minus integral v du. So 2/5 x to the 5 halves ln of x minus v du, so minus the integral of 2/5 x to the 5 halves times 1 over x. Now that 2/5 can factor out of the integral. And your exponents subtract. X to the 5 halves over x is x to the 3 halves. And the antiderivative of x to the 3 halves is 2/5 x to the 5 halves. Plus c, and then multiply those 2/5, and your final answer is 2/5 x to the 5 halves ln x minus 4/25 x to the 5 halves plus c. Now next, this one feels as if there isn't enough stuff here to do integration by parts, but there actually is. You have to let one of the pieces be dx. And since you don't know how to anti-differentiate arctan, you have to let that be your u. So u will equal arctan of 3x. du is 1 over 1 plus the quantity 3x squared times 3 dx. Or, in other words, du is 3 dx over 1 plus 9x squared. And then dv is just equal to dx, so v is equal to x. Alright, so our integral is uv minus integral v du. So uv will be x arctan 3x minus v du. So when that x multiplies by du, we get a 3x in the numerator. We get a 1 plus 9x squared in the denominator. There you go. Now this is probably how you'll get tested on u substitution, because to finish this integral off, you have to use a substitution. And I've already used the letter u, so let's use a new one. Let's use w. So we're going to substitute for the entire denominator. 1 plus 9x squared. Then dw is 18x dx, or an 18th dw equals x dx. So that's x arctan of 3x minus 3 over 18 integral 1 over w dw. Now 3 over 18 reduces to a 1/6. So minus a 1/6. And the antiderivative of 1 over w is ln absolute value w plus c. And let's just insert what w was. W was 1 plus 9x squared. Now note that technically at this step, you don't actually need those absolute values, because 1 plus 9x squared is a positive quantity all the time. I'm not going to dock you if you drop them, if you don't drop them, but it's just nice to notice that you can. All right, next we have one of these tricky round-the-world problems. And how you can tell that you have that is you have a combination of e's and sines or e's and cosines. There's other instances in which this happens as well, but this is a pretty big giveaway. So I'm going to let u equal the thing I want to differentiate. I prefer to not have fractions. I'm going to let u equal e to the 2x. And then du is twice e to the 2x. Now dv is going to equal sine x dx, and the antiderivative of that will be negative cosine. So this will equal uv minus the integral of v du. So uv will be e to the 2x times negative cosine x. So negative e to the 2x cosine x. Now v du will have minus the integral of negative 2 e to the 2x cosine x dx. Notice that double negative will cancel and make a positive, and that 2 can factor out of the integrand. Okay, and let's do it round 2 one more time. Let u equal e to the 2x. Du is 2 e to the 2x. dv is cosine x. And the antiderivative of cosine is plain old sine. So the negative e to the 2x just hangs out. Plus twice. Now the second part expands into uv. So e to the 2x sine x minus the integral of v du. So I'm just going to pull that 2 out right away. Minus 2 integral e to the 2x sine x dx. Then this 2 outside the parentheses must distribute. And we are at negative e to the 2x cosine x plus 2 e to the 2x sine x minus 4 integral e to the 2x sine x dx. At this point in time, you should realize that you are back where you started. You have the exact same expression inside your integrand as you had in the beginning. And so you add these to both sides. So you add 4 integrals of stuff to the 1 integral of stuff, and you get 5 integrals of stuff. Equals negative e to the 2x cosine x plus 2 e to the 2x sine x. And your final answer you divide by 5, and don't forget your plus c. So the integral of e to the 2x sine x dx is negative 1/5 e to the 2x cosine x plus 2/5 e to the 2x sine x plus c. Now this integral could be found by either letting u equal sine of theta or u equaling cosine theta. Both will work. But sine has a positive derivative, so I'm going to choose that one because I think it's a little bit easier. So if we decide to let u equal sine theta, let's figure out what we have to save. Du is cosine theta d theta. So we're going to take this integral and we're going to break it into the integral from 0 to pi halves sine cubed theta times cosine squared theta times cosine theta d theta. And that stuff is saved for later. The cosine squared becomes 1 minus sine squared. right, and now we also need to change our bounds. If you prefer to not do that, you must write like 0 equals theta, pi halves equals theta, but really it is faster and easier to change your bounds. Just give it a try, it's not that hard. This tells you, the lower bound tells you that theta is equal to 0, and using this substitution, if theta is 0, u is sine of 0, or 0, and if theta is pi halves, u is sine of pi halves, which is 1. So what that tells you is that area under the sine curve, that complicated sine curve between 0 and pi halves, is the same as the area from 0 to 1 underneath the curve u cubed 1 minus u squared. It just gives you a different way to find that area. And if you also did this side by side, one with changing the bounds, one with not, you'll see that in the end, what you're ending up with is something very similar to this. Then we just distribute and add exponents. So u to the third minus u to the fifth. So the antiderivative of u to the third is 1/4 u to the fourth minus a sixth u to the sixth, evaluated from 0 to 1. So that will give us 1/4 minus a sixth. A good common denominator is 12, so that will be what? 3/12 minus 2/12 is 1/12. Now you have to know when to use Pythagoreans, and you have to know when to use half-angle identities. And because this is sine to the fourth, the half-angle identity is your option. Don't go making up some weirdness integration by parts stuff. That's just harder. So half-angle. First, this is the same thing as sine squared of 5x. The whole thing squared. And then that sine squared of 5x is 1/2. 1 minus cosine of double the angle becomes 10x. That whole quantity squared. So the 1/2 is squared and becomes 1/4. And the 1 minus cosine 10x when it's squared becomes 1 minus 2 cosines of 10x plus cosine squared of 10x. And we can integrate every term except for this last one. So to this last one, we must again apply a trigonometric half-angle identity. So this will be 1/4 integral of 1 minus 2 cosine of 10x. Now cosine squared of 10x is the same thing as 1/2. 1 plus cosine of, now the angle doubles again and becomes 20x. And then adding this 1 to the 1/2 we get after distribution, we have 1/4 integral of 3/2 minus 2 cosine of 10x plus 1/2 cosine of 20x dx. And now you're in a position where you can integrate everything. So the antiderivative of 3/2 is 3/2 x. The antiderivative of cosine of 10x is 1/10 sine of 10x. Well, the 2 over 10 will make a fifth. So minus a fifth sine of 10x. And this, the antiderivative of cosine 20x will be 1/20th sine 20x. 1/20th times 1/2 will make 1/40th. Plus c. You can choose to or not to distribute that 1/4 at your discretion. You may also be asked to evaluate integrals that involve some combination of tangents and secants. So here you could let u equal tangent, but if you did, the derivative is secant squared, and you're left with a singular secant hanging out that you can't replace. So that means you have to try to let u equal secant, and after saving whatever you need to be your du, change the other tangents into secants. So u is secant, du is secant theta, tan theta, d theta. So that becomes the integral of tan to the fourth theta secant squared theta times secant theta tan theta d theta. Now tangent to the fourth, that can be replaced by secant squared minus 1, the quantity squared, and now we're ready to substitute. When we substitute u for secant theta, we have the antiderivative of u squared minus 1, the quantity squared, times u squared du, which is then the integral of, expanding that out, we get u to the fourth minus 2u squared plus 1. And then distribute the u squared, and we have the antiderivative of u to the sixth minus 2u to the fourth plus u squared du. Now let's antidifferentiate and plug our substitution back in just to save us some time. The antiderivative of u to the sixth is 1/7 u to the seventh, so the 1/7 secant to the seventh theta, minus the antiderivative of u to the fourth is u to the fifth over 5, so minus 2/5 secant to the fifth theta, and then plus the antiderivative of u squared will be 1/3 u cubed, so 1/3 secant cubed theta plus c. Alright, and this one, letting u equal secant will not work, because then your derivative is secant tan, and you're going to have a singular tangent, not a tangent squared to replace. So you're really hoping letting u equal tangent is going to work. If you let u equal tangent theta, your du is secant squared theta d theta. So think about breaking this into tan squared theta, secant squared theta, secant squared theta d theta. Now that part's being saved to be the du. Secant squared theta is tangent squared theta plus 1. Alright, times secant squared theta d theta. And now put on your u's. You have the integral of u squared plus 1 du, distribute integral of u to the fourth plus u squared, and that will be 1/5 tangent to the fifth theta plus 1/3 tan cubed theta plus c. Alright, next we have trigonometric substitutions, and these are tricky, so you probably won't be asked very many of these. So first of all, we have a number minus x squared, so we're going to somehow use a sign. Since it's 4 minus x squared, we're going to let x equal 2 sine of theta. And doing so, we get dx is 2 cosine theta d theta. So that becomes the integral of, so x squared is 4 sine squared theta. Dx is 2 cosine theta d theta. In my denominator, I'll have the root of 4 minus 4 sine squared theta, all that business cubed. So in the numerator, we have 8 sine squared theta cosine theta d theta. In the denominator, that 4 factors out. The whole thing is cubed. So that 1 minus sine squared, that is equal to cosine squared. So inside the cubed, we have 2 cosine theta over 2 cosine of theta, the quantity cubed. Notice that that 2 cubed makes 8, thereby canceling the 8 in the front. And this cosine cubed will cancel with one of those cosines, giving us just the integral of sine squared theta over cosine squared theta d theta. And sine squared over cosine squared, that's the integral of tangent squared. And that's not one of the things you know an antiderivative for quite, but you're awfully close. You know one for secant squared. And because of your trig identities, you know that you can make tangent squared into secant squared, because tangent squared is equal to secant squared theta minus 1. And now the antiderivative is tan theta minus theta plus c. And let's construct our triangle to change our thetas back into x's. X over 2 equals sine theta. So sine tells us the opposite side over the hypotenuse, making the adjacent side 4 minus x squared. So tangent is opposite over adjacent, so x over root 4 minus x squared. And theta will be arcsine of x over 2, or sine inverse x over 2 plus c. As always, those are rather tricky. Believe it or not, this one's going to involve a very similar trick. It's also definite, which I wanted to also mention. So first of all, we're going to let x equal secant theta because we have a variable squared minus 1. And then dx is secant theta tan theta d theta. And let's talk about how to change those bounds. So if 1 is equal to secant theta, I'm not so good at secant, I've got to make it back into cosines. That tells you that 1 is equal to 1 over cosine theta, which is the same thing as saying 1 is cosine theta. And the angle at which cosine is 1 is 0. There are many, but that's kind of the most common one. Then solving 2 equals secant theta, we have 2 equals 1 over cosine theta, and that means that cosine theta has to be a half. Now cosine is the x-coordinate on the unit circle, so is cosine 1/2 right here, or is it cosine 1/2 right there? And the latter is the answer. That's the angle pi thirds. In the particular instances of these cases, it's really, really, really nice to change your bounds and not have to go back to x's. There's no need to go back to the unit circle little triangle then, for example. So this becomes the integral from 0 to pi thirds. So inside the square root sign, we'll have secant squared theta minus 1. Outside it will have secant theta tan theta d theta, and in the denominator we're going to have a secant theta. So those secants cancel. Inside the root sign we have the integral 0 pi thirds. Inside the root sign we have tan squared times the tangent theta outside. So that just becomes the integral of tan squared theta from 0 to pi thirds. Remember that trick we did in the last example? This becomes the integral from 0 to pi thirds of secant squared theta minus 1 And the antiderivative of secant squared theta is tan theta minus theta. And now because you've changed your bounds, you can just plug in 0 and pi thirds. So you're going to have tangent pi thirds minus pi thirds minus tangent of 0 minus 0. Now tangent of pi thirds is sine of pi thirds divided by cosine of pi thirds. Sine of pi thirds is root 3 over 2. Cosine of pi thirds is a half. And root 3 over 2 over 1/2 is just root 3. So our final answer is root 3 minus pi thirds. The final integration technique we're going to review is integration by parts. So first, give the partial fraction decomposition for the following. So the first thing we have to check is the numerator's degree lower than the denominator's degree? Otherwise, you'd have to do long division. So in this case, it is. And notice that this is the same thing as x squared plus 4 over x times x plus 2, x minus 2. And that would expand into some constant a over x plus some constant b over x plus 2 plus some constant c over x minus 2. So that's the partial fraction decomposition, where a, b, and c are some constants. Next, we have x squared plus 4 over x squared times x minus 4. Notice that x squared is a repeated linear factor, so you have to have one constant over x plus another constant over x squared plus a final constant over x minus 4. And next we have x squared plus 1 over x times x squared plus 4. X squared plus 4 is an irreducible quadratic, so you'll need an, how is the big marker? You'll need an a over x, and you're going to need a bx plus c over x squared plus 4. You need a linear polynomial over that quadratic. All right, now we have sort of a simple one and a little bit more challenging one. So the simple one is when you can use that cover-up method to find the values of those coefficients. So first, factor that denominator. We have 1 over y minus 6 times y plus 2 is equal to a over y minus 6 plus b over y plus 2. Then multiplying by the y minus 6 and y plus 2, we get 1 equals a times y plus 2 plus b times y minus 6. And now if you input clever values, for example, if you input y equals negative 2, the term with the a goes away, and you get 1 equals negative 8b, b is negative 1/8. And if you input y equals 6, the term with the b goes away, and we have 1 equals 8a, and so a is positive 1/8. And with these kinds of problems, most of the work is in the algebra. So that tells us that this can be written as an 1/8 over y minus 6 plus negative 1/8 over y plus 2. And while we couldn't integrate the first thing, we can integrate each individual component of this. So the first one will have 1/8 natural log absolute value y minus 6, and then minus 1/8 natural log absolute value y plus 2 plus c. That plugging clever stuff in trick won't work when you have quadratic factors because those are never 0. You can't plug any number in to make them 0 because they never are. So, all right, well, this was going to be a little painful, but you can do it. So we have 3x cubed minus x squared plus 6x minus 4 over x squared plus 1 times x squared plus 2 is equal to ax plus b over x squared plus 1 plus cx plus d over x squared plus 2. And multiplying it out so the denominators go away, we'll have 3x cubed minus x squared plus 6x minus 4 equals ax plus b, that thing multiplied by the x squared plus 2, and the cx plus d multiplied by the x squared plus 1. I'm not going to rewrite the left side, it just takes so much space. So expand out the right side, and we have ax cubed plus 2ax plus bx squared plus 2b. And then the next expansion gives us cx cubed plus cx plus dx squared plus d. And let's just group the like terms. So first we have the cubes, that one and that one. So we'll have x cubed times a plus c. Then we have the squareds. So this one and this one, that'll be x squared times b plus d. Then we have the x's. So there, x times 2a plus c. And finally, we have the constants plus 2b plus d. And you have to recognize that this a plus c, that has to equal this 3 because it's the coefficient of the x cubed. So a plus c must equal 3. Then the b plus d, that has to equal the coefficient of the x squared, so that has to equal -1. The green thing, the 2a plus c, that will have to equal 6. And the constant, the 2b plus d, that will have to equal -4. Okay, now we're going to combine the red and the green one and then the orange and the blue one. So for this one, let's solve this for c. C is equal to 3 minus a. That can get subbed into there for c. 2a plus 3 minus a equals 6. So I think 2a minus a is just a. Take away that 3, you get a is 3. So awesome. And then if a is 3, well, c is 3 minus a, so c is equal to 0. Now similarly, combine this equation and this equation to find the values of b and d. So, well, d will equal -1 minus b. So take that and input it for the d. So 2b minus 1 minus b equals -4. So I think we get b equals -3. And then inputting that over here, d is equal to -1 plus 3, double negative. So d is 2. And then you're like, oh my gosh, I still have to integrate. So let's call this original integral something like I. That'll make it easier to rewrite the whole thing. So the original integral, I will equal the integral of ax plus b. So 3x minus 3 over x squared plus 1 plus cx plus d. So plus just 2 over x squared plus 2. All right, now that first integral will have to be broken into two parts. So specifically, meaning that it must be broken into 3x over x squared plus 1 minus 3 over x squared plus 1 plus 2 over x squared plus 2. And now everything here is not very bad. This first one, you could do a substitution for the denominator. You're going to end up with 3/2 ln absolute value x squared plus 1. The over 2 comes from the derivative of x squared being 2x. The antiderivative of 3 over x squared plus 1 is 3 tan inverse of x. And then the other one will be 2 over root 2 tan inverse x over root 2 plus c. Now we also need to know how to approximate things using the three different rules, the trapezoid rule, the midpoint rule, and Simpson's rule. And in this case, if I give you a complicated function, I'm just not going to ask you to simplify it. I'm just going to ask you to sort of give me an expression for what it is. So if we're estimating the area under the root x cosine x dx curve with n equals 8 between 0 and 4, first notice that your delta x, that's 4 minus 0 over 8, or 1/2. So for the trapezoid rule, T8, so we'll have 1/2 over 2, and then you have 1 of the first and the last, and then 2 of all the middles. So 0, root 0, cosine 0, plus twice root 1/2 cosine 1/2, plus twice root 1 cosine 1, you get the idea, dot, 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 plus the second to last thing you have will be 2 roots of 3.5 cosine of 3.5 plus root 4 cosine of 4. And if you want to work out what that is, it'll be approximately negative 2.364. All right, now let's use the midpoint rule to estimate the same thing. So notice that with your interval, your first subinterval goes from 0 to 1/2. The midpoint is 1/4 or 0.25. Then the next midpoint between 1/2 and 1 is 0.75. So that's the pattern. The points are spaced out 1/2 apart, starting at 0.25. So M4 will be delta x, which is 1/2, times root 0.25 cosine 0.25 plus root 0.75 cosine 0.75, etc. I get that you know the pattern. Now the last one is in between 4 and 3.5, so 3.75. Root 3.75 cosine 3.75. And if you approximate that with a calculator, you get it's approximately equal to negative 2.310. And the last approximation technique we have is Simpson's rule. Remember that Simpson's rule takes delta x over 3. So that will be 1/2 over 3, which notice that's actually 1/6. And then you have 1 of the first and last, so 0 cosine of 0. And then the stuff inside goes 4, 2, 4, 2. So plus 4 root 1/2 cosine 1/2 plus 2 root 1 cosine 1 plus 4 root 1.5 cosine 1.5. You kind of get the idea. This one's going to end on 4 root 3.5 cosine of 3.5 plus just root 4 cosine of 4. And that will be approximately equal to negative 2.328. The final topic, and I think kind of one of the neatest, is evaluating improper integrals. So we have two types, the type where one of the bounds is infinite, and then the type where you have an infinite discontinuity. This is the type with an infinite bound. So first you have to know how to use proper notation. So this is the same thing as the limit as b goes to infinity, the integral from 1 to b, and that is the same thing as 2x plus 1 to the negative third. And now let's antidifferentiate. So the antiderivative of 2x minus 1 to the negative thirds will be 2x plus 1 to the negative second over negative 2, and then times a 1/2 to kind of do the reverse chain rule, evaluated from 1 to b. So that becomes negative 1 over 4 2b plus 1 squared minus negative 1 over 4 times 2 plus 1, the quantity squared. Note that this first term, because b goes to infinity, that first term goes to 0. And then the second term, the double negatives cancel, giving us 1 over 4 times 9, or 1/36. Unless you're careful, you won't notice that this particular one has a problem. Notice that technically speaking, the function you're given is not continuous on the interval from 0 to 1, so you gotta be careful about that. So because 0 is the problem point, and you have to approach 0 from inside the interval, you have to come at it that way. So that would be 0 from the right. So this will equal the limit as b goes to 0 from the right, b to 1, and let's just break that up into x over root x minus 1 over root x, because we're going to have to do so to integrate anyway. So that becomes the limit as b goes to 0 plus integral from b to 1, x to the positive 1/2 minus x to the negative 1/2. Now the antiderivative of x to the 1/2 will be x to the 3/2 times 2/3 minus 2x to the positive 1/2 evaluated from 1 to b. So that will be 2/3 minus 2, plugging in 1 for both of those, minus 2/3 b to the 3/2 minus 2 root b. And at this point, plugging in b equals 0 doesn't give us a problem in either of those terms, so those two last terms on the end both go to 0. And we're left with 2/3 minus 2, which is 2/3 minus 6/3, or negative 4/3. And the review material in this chapter 7 begins in your book on page 537, and there's really a lot of good stuff there. The first thing is there's this thing called the concept check. So read it and make sure you understand all of the concepts listed there. It's one of the really awesome things that Stewart does, and they seem to hit all of the major ideas. So the true-false quiz also is pretty useful, and then I have a list of suggested problems that I would really suggest that you do, like they'd be pretty helpful. So those problems, they're all odds, and you can check your answers with the back of the book. And if you get stuck, make sure you ask for help. If you want to work some evens too, and you have a way to check your answers, like using Wolfram Alpha or a calculator, that's also a great idea. But those are the ones that I cherry-picked thinking they'd be specifically helpful.